Hello students. Next we will look into the properties of digital discrete time LTI system. That means we will be again talking about some of the properties of the system like system with memory, without memory, causality of a system, stability of a system, invertibility, all these things we will again revisit here, but this time we will see it with respect to the system equation h of n. That means we have already defined that a system will have an equation or it will have a function which is defined as h of n, and it will have an input and an output which is given as x of n and an output of y of n. Now that we have defined h of n and how x of n convolution with h of n gives y of n, now we will redefine these with respect to h of n. Okay, so we will start with the first one, which is a system with or without memory. Well, with respect to h of n, we can say that if h of n is having a non-zero value for all the values of n, which is, let us say for some n0 value, where for n0 not equal to 0, that means that is if h of n has values at n not equal to 0, that means n other than 0, if it is having some value, then in this case we will say that the system is with memory. The system is with memory. That means if you are having a system which is having h of n equation which is given by, let's say, 1 comma 2, or let's say hn is equal to 4 comma 3 comma 1 with arrow being here, since we have not drawn any arrow, automatically the arrow will be for the first one. So for this case you can see that the value of hn exists for all other times other than at the 0 axis. Okay, in this case we will say that the system is with memory. Then obviously a system without memory will have only values with at n is equal to 0. If h of n is not equal to 0 for n equal to 0, and h of n, let me write it in separate line, and h of n is equal to 0 for n not equal to 0, in this case we will say that the system is memoryless. The system is memoryless. So it means you will have only one value, and that value will be existing where? That value will be existing at that value will be existing only at 0, at 0 axis, at n is equal to 0. So that case the system is called as a memoryless system. Next we will look into the condition of causality, a causal system and a non-causal system. So we will look into the property of causality. So as you know, we have already seen this, but I will define that if h of n is equal to 0 for n less than 0, that means for all negative values of, for all negative values of n, if h of n is equal to 0, then the system is causal. That means it's a practical system. So the system is causal in that case. We have to look at a proof for it. Let us look at the proof for it. Basically, we know that if we have any system, the output y of n will be basically equal to x of n convolution with h of n, or we can say h of n convolution with x of n, which is basically, if you remember, this is one of the properties of convolution, which is the commutative property. So in that case, we will use the second one for the equation. We know that the equation is going to summation k is equal to minus infinity to infinity h of k x of n minus k. Now here, this particular equation y of n can be split apart into two equations. One is for the values of k is equal to minus infinity to minus 1, and the second part of the equation will be summation k is equal to 0 to infinity. So we have split up the the summation, and here the rest of the things will be as such. So h of k x of n minus k, and here it will be h of k x of n minus k. Now here with the values you can very clearly see that, if you would look at the values of x here, x of n minus of, see, all the values of k are going to be minus here. So minus of minus something will always become plus. So plus some number, let's say 2, let's say 1, let's say 2, 3, 4, 5, up to infinity, any numbers. Whereas here the values will be all x of n, minus of some positive values, 1, 2, or even 0, all those values. Let us say plus 1, so it is going to be x of n minus 1. We know that x of n plus 1 means these are all future values, correct? Whereas x of n minus 1 are all past values, the values that have already been in the past, whereas these are the values which only are going to be there in the future. Now what is a causal system? A causal system is a system whose output depends only on the past and present values and not on the future values, isn't it? So it means that in this particular equation, this part has to be totally equal to 0. Then only we can say that the system is going to have an output which depends on only past and present value and not on any future values. So to make that future values is equal to 0, the best thing is to basically make this h of k is equal to 0, h of k is equal to 0 for all the values of k in this particular equation. What are the values of k in this equation? K's value is all starting from minus 1 all the way up to minus infinity. That means for all the values of k less than 0, the system, if the value of h of n is going to be equal to 0, in that case y of n will not depend on future values, it will depend only on past values. So let me write that in the case as a statement. So the first summation is basically weighted sum of future values. Thus, for the output to be from a causal system, the first summation should be equal to 0, and the first summation, here it should be minus 1. Yeah. So minus infinity to minus 1 should be equal to 0, which will happen, that is h of n should be equal to 0 for all n less than equal to 0. That's what we can see here, isn't it? The k value is going to be all negative. That is what we have written. H of n should be 0 for all the values of n less than equal to 0. So this is the causality, property of the DT LTI system. Next, we will look into the stability of the system. So as per the definition, a discrete time LTI system will be BIBO stable. We have all seen what is BIBO. BIBO is basically bounded input, bounded output. So a system will be BIBO stable if h of n, so I will write that equation first, if the summation of h of k for all values of k going from minus infinity to infinity, if the absolute value of that and take the summation of that, if that is equal to 0, then the system is absolutely stable. So a discrete time LTI system is BIBO stable if this particular equation is followed, which is the summation of the impulse response is absolute. Absolute means its value is some value of not less than 0, I should write it as less than infinity, sorry, less than infinity. So let us look at the proof of the same. So we will start with the assumption that x of n is bounded. That means if I am going to look at the absolute value of x of n, the absolute value of x of n is always going to be less than or equal to k, okay, less than or equal to, let's say, k1, okay, because I'm going to use k. So less than or equal to k1 for all values of n. For all values of n, I will not put the bracket, for all values of n, okay. So this is the first thing that we will, the first equation that we will think. That means we are assuming that the input is bounded, then only we can say bounded input, bounded output, isn't it? Now we know that the output then will be, we know that the output equation is y of n, which is the summation of x of n with h of n, and the equation for that we all know is summation k is equal to minus infinity to infinity x of k h of n minus k. But suppose if I am going to do the commutative, I am going to use the commutative property. So suppose if I write h of n and x of n, in that case first it will be h of k x of n minus k, okay. If that is the case, then I can say that the summation of y of n, because I want to look that the output should be bounded, and we know that for bounded then the absolute value of y of n should also be bounded. So in that case, if I am trying to take the absolute value of y of n, then it's as good as taking the absolute value of the equation k is equal to minus infinity to infinity h of k x of n minus k, which is basically the summation. The summation, I will take it outside, so it is k is equal to minus infinity to infinity absolute value of h of k multiplied with the absolute value of x of n minus k, correct? But see, we have already seen here that each and every value of x of n will be less than some value k1. That means no value of x of n for any value of n will have a value which is greater than k1. That means x of n will never have a value which is greater than k1. So I can say that the absolute value of yn, which is basically the summation of the multiplication of these, out of which this value will never be greater than k1. So I can write, therefore, from equation 1, which is, I have put the limit. From equation 1, I can say that the absolute value of y of n will be less than or equal to the summation k is equal to minus infinity to infinity h of k, and here I am going to put k1, because I have already said that its value will never be more than k1, isn't it? That I have already said. So now I know that for Bibo stability the output should be bounded. So I will write for Bibo stability, y of n absolute value should be less than or equal to some, some value which is, less than infinity. So some value, let's say k2. Okay, in that case then the summation of k is equal to minus infinity to infinity h of k should also be, having some value which is less than infinity, then only this particular multiplication will result in a finite value which will give you some k2 value. So h of k, summation of this value, it cannot be greater than infinity, so it should also be less than infinity. So based on that we have proved that this is the condition. So this is the condition, hence proved. Next we will look into invertibility property of a DT LTI system. So what does invertibility say? It says that suppose if you are going to have a system, in which the input is x of n, the system is h of n, and the output coming out of that is y of n, and suppose that y of n we are going to put into another system, such that now the output comes out to be x of n itself. Okay, that means I have got the x of n back. If that is the case, then this system will be called as the inverse of the original system h of n. So I will write it as h superscript invert bracket n. So I am going to write it like h invert n. That means it is the invertible system h of n. If that is the case, then we will say that h of n is an invertible system, and the invertible system is, or the inverse system is, h inverse of n, such that if you pass the signal x of n, whatever is the output, that output will give you back x of n if you put these two in cascade. So how do we write the statement? A system is invertible if the cascade of a system h of n and its inverse h inverse of n gives us the input signal back. That means I will write the equation that we want to prove, and that is that if you have h of n and if you convolute it with h inverse of n, then it's as that answer should come to be an impulse signal. That means its value should have a 1 at n is equal to 0. This is the only condition. So we have to prove it. Let's prove. We'll prove it in a different page. So proof. Now its proof is very simple. It's not at all complicated. We already know that, if we are going to have a system, wherein the input signal is x of n, the output will be x of n convoluted with y of n, and that output, which one? X of n convoluted with h of n, that is the output y of n, correct? That y of n that y of n, as it is shown here, that y of n, when it passes through H inverse, what happens? That output, so I will convolute this with the second system, which is H inverse of n, and that should give me back the original input signal x of n, isn't it? But we already know that, if you convolute any signal with an impulse signal, you will get the original signal back. Where did we learn this? If you remember, if we have a system h of n and I want to know what is h of n, I already told you give the input delta n, then you will get at the output y of n, which is equal to h of n. Why does that happen? Because if you do delta n convoluted with h of n, the output will be h of n itself. So if you convolute any value with delta n, you will get the original value back. So here also, if you want to get the original x of n, you have to convolute x of n with h of n. If that is the case, then we can very clearly see that this portion, this convolution has to be a delta n. That is, h of n convoluted with h inverse of n should be equal to delta n. Then only, here if you would substitute with delta n, you will get h of n, you will get x of n back. So we have to get this. This is the condition, and that is proved. So hence proved. So this is the simple proof for invertibility. So we have done 4 properties of discrete time LTI system. So if you remember, throughout we have done for the case of we have done for the case of discrete time system, we have proved it, we have proved the convolution sum, then we looked at the properties of convolution sum. Now we have looked at the properties of DT LTI system. The same thing next we will do for continuous time system. Thank you.